So let's visualize the, the, the dynamics of a spinning rocket. So what's behind these two equations that we discussed before? So as you remember, the equations are coupled. This means that, I'll draw here the axis. If we have a perturbation on the y-axis, so well, that would be a perturbation on the x-axis. If we have a perturbation on the x-axis and we have this movement, if we have a spinning rocket, then it would also affect the y-axis. So we would have this motion. So that's why we don't talk about only the angle of attack without any subscripts, but we talk about the alpha x and the alpha y. So, as I told you before, the dynamics of a spinning rocket are the sum of two damped sinusoids. There was one sinusoid that we called the fast mode and one the slow mode. The slow mode was the one that described the movement in general. So it was let's say the primary movement, as I'll try to describe now with this pen, and then we had a rapid movement that was on top of this slow movement. So I'm going to try to show you now. So imagine this is a rocket and it's spinning on the z-axis, and when it faces a perturbation, say on the y-axis or on the x-axis, it's going to have this movement. It's going to have I'm not going to do the rolling moment, so you can imagine it. I'm just going to do it's going to cone around the z-axis, and this movement would be the primary movement, and we call this movement precession. All right, coning. And then the secondary movement is on top of this primary movement, and we call it nutation. So it's small circles around the coning movement. I don't know if you can appreciate it by. So we have the main movement, precession, and then the secondary movement, it's the nutation. I don't know if it's clear enough, but as you can see, the primary movement determines the main shape, main dynamics of the movement. It has a slower, has a larger inverse time constant than the second movement, the nutation. So it means that it dies off way after the nutation. Okay. So if a rocket starts to precess, it may be hard to correct. Yeah, it may be hard to get it back to its zero angle of attack for various reasons. So first of all, the inverse time constant for spinning rockets is lower, which means lower restoration rate. It's going to take longer for a rocket to restore if it's rolling, as we discussed before. So it's going to take longer for it to go to zero angle of attack, and then also we have another problem, that if we are flying below, if it's rolling below the natural frequency, but maybe if it's close to it, then the rocket might start feeling the effects of resonance. Sorry. So this means that maybe the rocket isn't spinning still at the natural frequency, but as we saw before, we still have a positive gain just before natural frequency and after. So maybe the rocket is rolling at half the natural frequency, but the perturbations are already being augmented. So maybe the rocket is precessing, and it has a small, for example, a small perturbation moment due to a thrust, small thrust misalignment. Well, this thrust misalignment, if the rocket is spinning at a zone which you have positive gain, well, it's gonna further destabilize and try to fight against the stabilization of the rocket. So that's probably what happened to Stratus 2. Stratus 2 was also a rocket that I guess they didn't put any spin control, of course, but it wasn't designed to spin either. That's my guess. And the rocket, I think it was designed to go up to 50 kilometers, and finally went to something like 21 kilometers. And if you see the video, it looks like it processed all the video during all the flight. You can check it. It should be like it spins all the time, but it spins wobbly. You can check it. So why it went from the design 50 kilometers to 21? Well, if it's processing all the time, the angle of attack is super high. Maybe it stays at a high angle of attack, and then the drag then is going to be really high. And for a supersonic rocket, if it's climbing steadily at an angle of attack, it's going to eat up all the energy. So that's my guess for Stratus 2. And for Stratus 3, well, as you can see, there's a video where they kind of simulated the last seconds of the Stratus 3. You can see it starts processing, and it doesn't stabilize. So it starts processing, and the angle of attack, the coning gets bigger and worse, at a point that it just blows up, because it's still gaining roll in the final seconds, because it's still accelerating. I think the motor burn was 20 something seconds, and the motor was still burning. So you were still getting roll rate, higher roll rate. As you saw in previous videos, the natural frequency was still going down. So it was processing, it was getting worse and worse. So it went from coning, and yeah, at some point maybe it just hit an angle of attack that was too large, or it just hit natural frequency and just blew up. But the thing is, it didn't stabilize because it was already pretty near natural frequency. So any kind of perturbations were not helping to get the rocket back to track. So yeah, that's all I wanted to say.